So thank you. So my talk is somehow a continuation of Raphael's talk yesterday. But our viewpoint might be somehow different. Now let's look at the so-called restriction problem. That is, suppose I have a group G, which is a bigger group, and you have a smaller group, which is H, which is taken in two groups, and take a representation pi here, and take a representation sigma here. Now the restriction problem asks that does this pi restricted to 8, does the sigma appear in pi restricted to H? In other words, is this space, the home space from pi restricted to H sigma, 0 or not? That's this so-called restriction problem. And if you a better way to formulate this might be you consider all the H invariant linear forms on pi tensor sigma dual into C, and you ask if this is 0 or not. Now, if I ask the question in this generality, it's basically there's no hope that you can answer this question in this generality. But if we take some particular groups G and H, and take some particular representations pi and sigma, this might be doable. And the particular interesting case happens if this space is one-dimensional. And in that case, you might be asking, well, can you construct a generator of this? Now, the groups that we take are generally the unitary groups. Now, let's take E over F. This is a quadratic extension of number fields, and we take V. This is an n-dimensional skew Hermitian space over E, and we consider this unitary group U of V, which is defined over F. Now this is a unitary group defined over F over F. Now that is the group, and the representation here that we take are the following. We take pi 1 and pi 2. These are two irreducible cuspidal automorphic representations of U of V, A of F. Well, if you don't know what these things are, it's basically the direct summand. The direct summand of this space, the L2 space of this miracle quotient, and with some additional analytic properties. Now, so here we want to study this. So somehow we construct this. So define. This is the so-called Fourier-Jacobi period. That is, you choose phi1 inside pi 1 and phi2 inside pi 2. These are two functions on this unitary group, and we consider this so-called period integral. That is phi1 of G, phi2 of G, and theta function on the unitary group. So that's a theta function. And the integration is over this. Now, the way that you should view this period integral is that this is a function on the unitary group, which is basically this the sigma here, and in this part, you should view this as the functions on the Jacobi group. Well, here, let's say, suppose this is the unitary group in n plus 1 variables, n plus 2 variables. And here, inside here, you got this, this part is u of v, then that's this inside part, and then this Jacobi group is just this unitary group plus this this unipotent part, and this unitary group is the reductive part of the. Theta function is this and u1. Yeah, because it's just a u1. I mean, it's omitted. Now. Now, so this restriction problem is really that I take this G to be the Jacobi group and this H to be the reductive part of this, and I take that to be an element inside here, and I take this this one to be an element here, and I'm asking if this period integral non-zero or not. And well, of course, in order that this thing is zero, is non-zero, this representation space has to be non-zero. Otherwise, that integral vanishes for trivial reasons. So now the theorem, or the theorem, is the following. That is, to check this. Now I consider the absolute value square of this, then I should say that under some assumptions, which I cannot specify here, it's a long list of assumptions. Basically, at this place, this representation is assumed to be supercuspidal. At that place, it's the place splits or something like this. Now, now the absolute value square of this consists of three parts. The first one is a quarter, and the second part is some L function. The interesting part is this. Some other non-central values, times a product of a bunch of local linear forms.
The local part that depends on the choice if you want to do the other part, I mean the local.
Yeah, right. So this local part is that's basically the local linear forms on these things. Now, if you look at this formula, all right, this mu here, this right, this mu here is a character used to define the theta function. So in defining the theta function, you need to choose some characters, and this mu is one of it.
B some base change.
This BC of this stands for the standard base change. Now, if you look at this formula here, so the non-vanishing of this basically, so this part is non-vanishing, and this part is not identically zero precisely when the space is not zero, and then the non-vanishing of this period now is governed just by the central value of this L function. How much time do I have?
6 minutes.
Oh, I'm going pretty fast. That would take much more than 6 minutes.
Why do you take this particular function on the where you put a Jacobi, I think? I mean, is that in some sense a general?
What is general?
Theta series. Why did you choose something like that?
So because any automorphic form on any automorphic representation. Now, where's the Jacobi group? Any automorphic representation on the Jacobi group would be something like something like this, where this is the automorphic representation of this inside part, and that is a wave representation on that part. And if you if you restrict this whole thing into this reductive part, it basically becomes this. Now here here basically the larger group, this G is the Jacobi group, and this H is the reductive part. The picture is like this. Well, there's another situation, that is, you can embed this, as I said here, and this whole thing is just the unitary groups, the unitary grouping n plus 2 variables, and then you can embed this here, and take this to be the larger group, and this Jacobi group to be the smaller group. However, it turned out that this situation seems to be much harder somehow. Now, still, you can form the period integrals like that. That is, you take you take automorphic representation here, and the theta function on this whole Jacobi group, and plus an automorphic form on this group, and then you multiply them, and then take the and then integrate. And in that case, it would be much harder to obtain such a formula, except in some lower rank cases, and the case of U3. So the case of n equals 1 seems to be workable in some cases. That is, suppose you take endoscopic forms from here and restrict this to the Jacobi group, then at least in this case, I think you can obtain such a formula. Still, in that case, the non-vanishing of the period is governed by the central value of the corresponding L function. Yeah, maybe I can stop here.
Thank you very much.